In this video, we're going to take a look at how to find formulas for a variety of compounds by experimentation. So far we've been studying molecular and empirical formulas, and we kind of just told you, by experiment we figured out that there were so many grams of this element and so many grams of that element. But now we're going to see what actual experiments are done in order to do that. I'm going to briefly introduce you to one type of experiment, and then we're going to focus more on another type for determining the formula of hydrates, which you actually already learned how to name in one of the first units. So we're not going to spend too much time on this one here. This is called a carbon-hydrogen combustion analyzer, and it's a way to find how much carbon and hydrogen there is in a compound that you might be studying. So let's say you're studying this compound here, CXHY. You don't know what the X and the Y are, and that's our skeleton formula. We would need to figure out what mass of carbon and hydrogen are in there. So what we do is we do this reaction called a combustion reaction, which you've seen before. You take your hydrocarbon, your CXHY, combine it with oxygen, and it produces some CO2 and some water. And so what I want you to understand here is that all the carbon that was in the hydrocarbon is now going to be in the carbon dioxide, and all the hydrogen that was in the hydrocarbon is now going to be in the water. Now, using your knowledge of percentage composition and mass percent, you could figure out the mass percent of carbon in carbon dioxide, the mass percent of hydrogen in water, and then you could figure out, well, what mass of carbon and hydrogen there must have been in the overall compound. So this picture here is just an example of the combustion analysis, the combustion analyzer. You put your sample of CH or fuel in here, the thing you don't know, your CXHY, and then you basically put it through the machine, and you get the water that's made as absorbed, the carbon dioxide that's made as absorbed, and if there's any other substances that are produced as a byproduct, they might be released. But the main idea is that we take the water, we take the carbon dioxide, we use our mass percent and our percentage composition, and we figure out how much hydrogen and carbon there was, and then we can use that in order to figure out, well, an empirical formula. And then if we want, we can figure out the molar mass of our compound using a mass spectrometer, and then we can compare the two to get the molecular formula. And there we have it. We get our formula for a compound, and therefore the identity. So that's the general idea behind a carbon-hydrogen combustion analysis or analyzer. I just want you to get the general idea behind it and how it works, so that you know it's not really magic. It does happen through experimentation, and we need that experimentation in order to analyze these compounds. And so we can use these combustion analysis machines in things like the pharmaceutical industry to figure out, well, what is in our medication, the food industry, the food chemistry industry, forensics, or academic research when we're trying to figure out what the unknown compound is, or get some idea as to what the unknown compound is. What we are going to focus on more is going to be figuring out the formula of a hydrate. But if you're interested in working through problems with combustion analysis, you can do some sample problems that I've included in the notes in the PowerPoint here. Feel free to go through them, follow the steps. They're not super challenging. It's just if you want a bit more depth in your studies, you can go ahead and try this one here, and it might actually allow you to understand the concept of mass percent, percentage composition, empirical formula, and molecular formula in a bit more detail and depth. And here's another sample problem relating to the combustion analysis. So now we get to hydrates. You already know what a hydrate is. It's an ionic compound with some water molecules attached to it. And so we're just going to do a quick review of how to name hydrates and how to write formulas for hydrates. And then afterwards we're going to see how do you figure out, well, how many water molecules are attached to your ionic compound. So we'll start off with naming hydrates. So let's say we had MgSO4.5H2O. Your first step is to name the ionic compound first. So we have magnesium sulfate, magnesium sulfate, and your second step is to choose the Greek prefix that matches the number that's in front of the water. So mono is 1, di is 2, tri is 3, tetra is 4, 5 would be penta. So we're going to choose penta over here. And to indicate that it's water, we're going to write hydrate afterwards. So what we do is we combine these together. We have magnesium sulfate and then we have 5 waters attached to it. So that's going to be penta hydrate. So you can practice naming these ones here. What I would do is try to write out the answers and then pause my video, try to write out the answers, and then you can listen to my answers. So this one here would be lithium oxide dihydrate, potassium oxide trihydrate, calcium chloride hexahydrate. So you also have to know how to write formulas for hydrates. Let's say, for example, we had sodium carbonate decahydrate. First, what you do is you write the formula for the ionic compound, sodium carbonate. That part there is the ionic compound. You have to go back and review those rules. So we have Na2CO3. That's the sodium carbonate. Then you go and take a look at the prefix in front of the hydrate. It's deca. Deca means 10. So that means there are 10 water molecules, or 10 moles of water molecules. That's what that can mean as well. So what we can do now is we can write out our formula. What you do is you first write out the formula for the ionic compound, then you place a dot, then you write that letter 10, or number 10, and then you put your H2O. So in your compound, for every Na2CO3 that you have 10 H2Os attached to it. Or you could also say for every mole, 1 mole of Na2CO3, you have 10 moles of H2O. So you can try out the questions below here. Pause the video, then you can check your answers. So here we'd have CuSO4.5H2O. And if you don't remember how to write down those formulas, you got to go back and review. Here we'd have CaSO4.2H2O. And here we'd have Na2SO4.10H2O. So quickly review how to name hydrates and how to write formulas for hydrates, because you will need to understand that in order to do the problems that involve hydrate and their formulas. If a compound does not have water attached to it, the technical name that we give to it is the anhydrous version of it. So for example, CaSO4 without water attached to it is anhydrous calcium sulfate. So sometimes you'll see that written on bottles. It means calcium sulfate without water attached to it. Whereas CaSO4.H2O, that's the hydrated version. That's the hydrate. So that's our calcium sulfate dihydrate. And you can write that out over here because you know how to name these now. So the non-hydrated version is called the anhydrous. And we don't always put it. Sometimes it's just implied if we don't say the hydrate portion of it. But now what's important is that you know how to calculate the molar mass of hydrates. So when you calculate the molar mass of hydrates, it's similar to what you've done before for molar masses. It's just that you now have to consider the molar mass of water. So for the molar mass of a hydrate, you first calculate the molar mass of the ionic compound that's attached to your hydrate. And then afterwards, you calculate the molar mass of water and add it, but you have to make sure it's the molar mass of the correct numbers of water. So if I have, let's say, 3 waters, I have to do molar mass of water times 3. If I have 2 waters, molar mass of water times 2. So we'll do this sample problem here together. We have calcium sulfate dihydrate. To find the molar mass, you first find the molar mass of calcium sulfate, and then the molar mass of water, and multiply the molar mass of water by 2. Don't multiply the whole molar mass of everything by 2, just the molar mass of the water, and then you add it to get to the molar mass of the calcium sulfate. So I'm going to find the molar mass of calcium sulfate first, looking at my periodic table. So we have 40.08 plus 32.07 for sulfur, plus 4 times 16.00 for oxygen. So we have 136.15 grams per mole from the calcium sulfate. And then we're going to add our water, so 2 times the molar mass of water. So molar mass of water would be 2.02, that's for the 2 hydrogens, plus the 16.00, that's 18.02. Grams per mole. So you do 2 times 18.02, and then you add the 136.15, and that gives you the molar mass of the hydrated version. And it makes sense, the hydrated version should be heavier than the anhydrous because you have water attached to it. The anhydrous, so if you just had the calcium sulfate, it would be lighter. It would be 136.15 grams per mole because you only have calcium sulfate. But when you attach 2 waters, now you have the mass, the molar mass of the 2 waters attached to it, and so that's what makes it a little bit heavier. So here there's some practice problems that you can attempt. You have a few different hydrates that are shown, and what I want you to do is figure out their chemical name. If I have a box next to it, some of them have common names that you may have heard of before. So for example, this magnesium sulfate heptahydrate is actually Epsom salts that you might sometimes put in your bath to soothe some wounds or to relax. So I want you to, again, try naming these ones here. Now, the other thing I want you to try is this little thought experiment here. So suppose you have magnesium sulfate heptahydrate, so the Epsom salt, in the prep room, and you want to do an experiment, but the experiment doesn't want the hydrate, it wants the anhydrous version, it wants the magnesium sulfate. How do you think you could remove the water from the magnesium sulfate heptahydrate? So pause the video, think about it, and then you can listen to my explanation. So hopefully you paused the video and you thought about it for a bit, and that you basically realize that you'd like to heat it up. You would heat up the magnesium sulfate heptahydrate so that the water that's present would evaporate away. And I'm sure you've actually done this experiment in class in one of the first units where you had a hydrate, you heated it up, and it went from a blue color to a white color, and that's because the water was leaving. So you'd have your magnesium sulfate now separated from the water vapor. It looks something like this. So I just wrote a little equation here, and I wrote a skeleton. Here I wrote a balanced equation, but the question was asking for a skeleton equation, which means not balanced. But the idea here is that, again, you had this, which started off as a solid, and after you heat it, the magnesium sulfate is a solid, but your water evaporated away, so that's in its gas form. And then you might have had crystals change color. Sometimes you have hydrates that are the same color before and after, and sometimes you don't. And so you'd have to figure out, if you had a hydrate that didn't change colors, how you would know the water was leaving. So pause the video and think about that. If you had a hydrate that did not change colors, it was the same color before and after, how would you know water left? Think about the molar mass example that we just did. So pause the video, think about it. Hopefully you pause the video and you thought about it and you realize that if water leaves, the mass should go down. So you could monitor the mass of your hydrate to make sure that water is leaving as you heat it up. So now what we're going to do is we're going to take a look at a sample problem where you have a hydrate. The problem is you don't know which hydrate it is. You don't know if it's a heptahydrate, decahydrate, dihydrate, trihydrate, monohydrate, whatever. You don't know what it is, but you've done an experiment and you want to figure out how many water molecules are attached to every ionic compound, or how many moles of water molecules there's attached to every mole of ionic compound. So here we have a hydrate of a compound, of barium hydroxide. We don't know what the hydrate is. We just know it's barium hydroxide X hydrate, XH2O. We want to figure out what this X over here is. And so there's additional information given about that hydrate, but the main point is that we want to find out what the X is. So you have a 50-gram sample of the hydrate, and we know that there's 27.2 grams of barium hydroxide in that hydrate. And so hopefully you're getting the idea that if there's a 50-gram sample and there's 27.2 grams of barium hydroxide in there, the rest of the mass must be due to the water. So your first step here is to figure out, well, what's the mass of water in that compound? So to find the mass of water in that compound, you simply do the mass of the total mass of the compound, so 50 grams. And what I'm going to do is I'm going to just add significant digits here to make sure we are practicing our significant digits. So I'm just going to put 50.0 grams. I'm just going to assume that we had a bit more precision. And don't do that when I give you a question, but I'm just doing it here to explain significant digits. So 27.2 grams here. We take away the 27.2 grams because that's our barium hydroxide, and that should give us the mass of the water because the rest of it must be water. So 50.0 minus 27.2, and we get 22.8 grams. So 22.8 grams of water. So now what we want to do is we want to find the mass percent of water. That's what our question was really asking. Find the percent by mass of water in the compound. So basically it's if the total of your test was 50 and you got 22.8 out of 50, what's that percentage? So you're simply doing the mass of water in grams divided by the total mass of the compound. If you already had the formula, you could actually figure out the mass percent of water by doing the molar mass technique. You'd find the molar mass of the whole thing, molar mass of water times how many waters there are, and then divide it by the total mass. So what we're going to do here is we're going to do our 22.8 grams divided by 50.0 grams, cross grams out, multiply it by 100%, and let's put that in our calculator. So 22.8 divided by 50 times 100, we get 45.6 grams, or 0.6%, sorry. 45.6% of the hydrate by mass is water. So the next part is finding the X value in the hydrate. We want to know how many moles of water are there actually in there. So what we do is we find the moles of each chemical within it. So we know our mole formula is going to be N is equal to mass over molar mass. So we take our mass of barium hydroxide, which was 27.2 grams, and we divide it by the molar mass of barium hydroxide. So you can find your molar mass of barium hydroxide, so 16.0 plus 1.01 times 2, because there's 2 of those, plus the molar mass of barium. Let me find it here. It should be in group 2. And we get about 171.3 171.31. I'm using a different periodic table than you might be using, so we might be a little off in terms of the decimals, but it's no big deal. It should be okay for this question, I'm hoping. So we write down our answer. We get 27.2 divided by that molar mass, and we get 0.1587. Now, we only have 3 sig figs, so really I should be keeping 3 sig figs, so 0.159, but I'm only writing that down for show, to show that I understand my sig figs. But in reality, try to keep a few of those digits in your calculator so that you're not rounding too much, and your rounding near the end is going to be more accurate for the problem in question here. So 0.159 moles. But keep a few more digits, again, because it makes our answers easier to get at the end. We're going to do the same thing for water, find the moles of water. So our mass of water was 22.8 grams, divided by the molar mass of water, which is 18.02 grams per mole. cross grams out, and you're left with moles in the end. So let's do that. 22.8 divided by 18.02, and we get 1.2 7 or 1.265. Again, keep some of those digits in your calculator. I'm just doing this for show to show that I know my significant digits here. Now what we want to do is we want to use these mole values as coefficients. So I'm going to put my 0.159 here. Or as you can see below, I kept a few more digits just to make this a bit easier for me. And then my H2O, my 1.27 over here. And this is just like we did with the molecular and empirical formulas. We have to divide by the smallest. So we divide by the smallest mole, which is 0.159. We want the simplest whole number ratio. It can't be a decimal ratio. Same thing here, divide here. And the end result is we get something like this. 1 here and 7.97 here. Remember our rounding rules. If you're 0.85 and higher, you can round up. If you're 0.15 and lower, you can round down. Here we're 0.97, so that means we can round up. This 7.97 can become 8. So the value of our x is 8. And so since the value of our x is 8, we know we have barium hydroxide, octahydrate. Now you can always check your answer by finding the mass percent of water using the molar mass method. So I'm going to quickly show you how to do that up here. So we know that our compound is now BaOH2.8 H2O. Now we know that the mass percent of water needs to be 45.6%. Let's see if that's the case. Let's do the molar mass of the entire compound. Molar mass of this entire compound, of this here, is going to be equal to our molar mass of the BaOH2, which is 171.31, plus the molar mass of water, which was 18.02, but it has to be times 8 because there's 8 waters, right? So let's do that. So let's do our 18.02, which is water, times 8, plus the molar mass of our barium hydroxide. We don't have to do times 8 there because there's only one barium hydroxide, 171.31. We get a molar mass of 315.47 grams per mole. And so now I'm going to find the mass percent of water. So mass percent H2O is going to be the molar mass of water times 8. So molar mass of H2O, I'm going to put 8 molar mass H2O divided by the molar mass of the entire compound, 315.47 grams per mole. Since they're both in grams per mole, the grams per mole will cancel out. Or you could assume, remember, a mole of the compound, and then you get grams, right? Assume a mole of the compound, times 100%. And let's see what we get. So we have 8 times 18.02 divided by our 315, multiply it by 100, and again, I get to about 45.6%. So that means that we found the correct formula. If I had a different number there, if I had 7, the mass percent of water would not have been 45.6% like we found in the initial problem. Okay, if I had 6, it would not have been the same. It would have been lower and lower and lower. So we want to make sure that at the end, our percent composition, our mass percent of water, matches the mass percent of water that we calculated initially from the data that was provided in the question. And that's a great way to check your work. If you can become efficient at doing that, then your work is more efficient and more effective, and you can see that your work is actually done correctly. So that's how to find the formula of a hydrate from some mass data. Basically, the scientists took the hydrate, the barium hydroxide XH2O, they heated it up a few times until they saw that the mass stopped dropping. Because what would happen is the mass would go down, and if the color doesn't change, you just have to keep heating it up until the mass stopped changing. So let's say it's at 100 grams, and the mass drops to 90 grams, so you lost 10 grams of water. You decide to heat it up again, and it dropped to 85 grams. So that means there was still water to lose. Eventually, you'll get to a point where you keep on trying to heat it up, and you keep reweighing it, and the mass won't change much at all. When that happens, then that means you got rid of all the water because nothing else is leaving. Even if you do have something that changes color, there might be some color left in between that you couldn't see. So it's always great to heat it up, weigh it, heat it up, wait again, heat it up, wait again, until the mass stops changing. And that way you'll get a good, accurate reading, as opposed to just assuming all the water's gone without actually knowing that it's gone. And that's going to be important because one of your labs for this unit is actually going to be to determine the formula of a hydrate using the method that I just described. So you will have some more practice problems to attempt. You can see the solutions that are given to you here. And then you have some more practice problems here. The solutions to the practice problems that are here are at the bottom. So, well, not the solution, but the answers, so you can check your work. If the sig figs are off, I do apologize. Just make sure that you do have appropriate significant figures. And there's also a worksheet that you should be provided with that might be in the Google Drive or that might be printed for you. Just make sure that you attempt these problems as well. On the next few slides, there's also some lab type questions that you might see. There's a virtual lab that you can attempt to make sure you understand how the lab works that you'll be doing sometime throughout the unit. So make sure you take a look at the virtual lab and the practice problem. I'm quickly going to go and walk you through it just to make sure you understand what you need to do. So here we have the virtual lab that you can attempt. You have a hydrate, you heat it up, and you can see that it goes from blue to white. And in the virtual lab, you can take a look at the mass of the water that escapes, and you can understand the concept that we did together. Notice that if you add water to the anhydrous, then it goes back and becomes blue again because now the water reattaches to the anhydrous to become the hydrate again. So do view the animation. And there's also a great virtual version of the lab where you can see the type of data that you'll be collecting, and you want to understand why you're collecting the data and how you're using that data to figure out the formula of the hydrate. So make sure that you take a look at both these links. Chances are that you may see a question on your quiz regarding the lab that you're doing with hydrates. This question here is another great one. It's from an old examination. So there's a link here to, first of all, a YouTube video to show you how the lab works. So here you have a crucible sitting on a clay triangle, which is sitting on an iron ring, which is attached to our retort stand. And then we have a Bunsen burner below. And here you can see the crucible tong. So look at that, we're practicing our chemistry materials. And then what you do is you put your hydrate in the crucible because it can withstand a lot of heat, unless there's cracks in it, of course, but it can withstand a lot of heat. You heat it up, you weigh it over and over again, and you basically monitor the mass. So you can take a look at the data that's provided here. You can see that first you weighed the empty container, the empty crucible, and then you put a sample in the crucible. And so you weighed the crucible with the sample, and you know what your sample size should be by subtracting the mass, right? So just to ignore decimals from now, if I had 22 gram container, I put a sample in it, and now it's 25 grams, you should know that, okay, that's 3 grams, because I do 25 minus 3, so 25 minus 22, that's 3 grams of sample. And then, so what I do is I heat it, and I go and take a look at I reweigh it after I heat it once, and I noticed that the mass dropped. It dropped from 25 to 23.982. So that means some water left, but I'm not sure if all of it left. So what I'll do is I'll go back and I'll heat it again, and I'll notice that the mass drops again to 23.976 grams. So it went from 25 to 23.92 to 23.976. And then I'll heat it one more time, and then I go and reweigh it, and I notice that, you know what, it didn't really drop that much anymore. It actually went up a little bit. It kind of, it fluctuates a bit. So since it's not really dropping anymore, then chances are I got rid of most of my water. So now I'm good at trying to figure out, well, what the molar mass of my, what the X value in my hydrate is. So in this problem, you need to first of all answer the question. So explain why the student can correctly conclude the hydrate was heated a sufficient number of times in the experiment. Use the data above to calculate the total number of moles of water lost when the sample was heated, and determine the formula of the hydrated compound. So basically, figure out what this N value is here to write down a formula for the hydrated compound. And then you have a little bit of a thinking question, an extension question. A different student heats the hydrate in an uncovered crucible, and some of the solid spatters out of the crucible. This spattering will have what effect on the calculated mass of the water lost by the hydrate? Justify your answer. There is a solution provided here, but don't jump straight to the solution. You need to try it yourself first. Think about this question. Think about how that will affect your data. Okay, you need to be a thinker. You don't need to be someone who just regurgitates information. Otherwise, when you get to a test and you see something slightly different, you're not going to get the right answer. You're not going to be able to face that that challenge. So try these out without looking at the solution. Then when you're done, you can go take a look at the solution and see how it's marked.